Today I want to talk a little bit about Louis de Broglie, who is another scientist who was looking at this kind of wave-particle duality. And again, the physicists in the audience are going to hate the idea of wave-particle duality, but it's kind of a simplified view of the physics of things, and it really does help us to understand, or at least to start to understand, what quantum mechanics is all about, because quantum mechanics gives us all this really wacky information about how particles can act like waves and waves can act like particles and energy is quantized. And so from all of that come very observable phenomena, very measurable phenomena, but it's really hard to get your head around conceptually. So we're going to talk a little bit about the de Broglie relation in this video, and I'll work a problem where we calculate the wavelength of a gigantic particle, which is just sort of improbable. So Louis de Broglie obviously is a French physicist, and the de Broglie relation is looking at the relationship between a particle with some sort of mass that is in motion and its wavelength. So the premise here is that if light, which we know is a wave, its energy, can act like a particle, which for light we call a photon, that's a discrete packet of light energy, then maybe all particles can act like waves. That kind of makes sense, right? You know, if this is true, then maybe it's true for all of these other cases as well. Now we'll find that that isn't 100% true. Not all particles can act like waves, at least in some sort of physical, there's some physical constraints that go into that. And I'll leave some of those physical restraints to the physicists, but we can talk a little bit about it, at least in terms of the math. And as chemists, we're looking at particles kind of on the subatomic level. We're thinking electrons, really. When you get up into protons and neutrons, even those are a little bit too big. So we're really talking electrons here. But let's talk the de Broglie relation. This is lambda, which of course is our wavelength. And so he said that the wavelength of light, or the wavelength of energy that is produced by this particle, or that is this particle, right? It's not produced by it, is. They are the same thing. They are one and the same. Are related by Planck's constant, which we know is 6.63 times 10 to the negative 34th joule seconds. And then the mass of the particle. And mass here, it's helpful for this to be in kilograms, which of course is our SI unit, so that makes sense. And then V here, this is a V, not a Greek nu, right? Greek nu is frequency, V is velocity. And units on that are going to be in meters per second. So the implication of this relationship is that the wavelength is only measurable, only observable if this particle is in motion. So that velocity implies that the particle has to be moving in order for us to understand and be able to talk about its wave behavior. Okay, so that's the de Broglie relation. So let's apply this to a particle. Let's work a problem here. We have a particle with a mass of 1.0 times 10 to the negative 6 kilograms. Now this is quite large for a particle. If we're comparing this to something like an electron, that's on the order of 10 to the negative 31 kilograms. So this thing is gigantic compared to our subatomic particles. So this thing is gigantic, and it's moving at a speed of 2.0 times 10 to the third, so 2,000 meters per second. So it's large, it's moving pretty quickly. What is the wavelength of the particle? So we're given our speed, our velocity, we're given our mass, we know Planck's constant, so we can plug it into our relationship. So here's our de Broglie relation with our h over mv. H, of course, Planck's constant, 6.63 times 10 to the negative 34th. Units on that are in joule seconds. And our mass here is given 1 times 10 to the negative 6 kilograms, and we're going to multiply that by our speed, which is our 2.0 times 10 to the third meters per second, or our velocity. V for velocity. Okay, so when I plug this in, then I end up with, and it looks like we're going to have 3 sig figs. I'm guessing this thing is going to be pretty small, right? Then I end up with 3.32 times 10 to the negative 31 meters. And we know it's going to be meters for a couple different reasons. Meters because it's wavelength, right? And then we can do some unit analysis here to make sure that this really gives us a meter like we're expecting it to. So let's think. A joule is really a kilogram meter squared per second squared. So on the top, I have a kilogram meter squared per second squared times a second. And then I'm dividing that by a kilogram meter per second on the bottom. So if we're analyzing this to see kind of how these things divide out, then my seconds here will divide out with this guy, this second will divide out with this one, then my kilograms will divide out, my meter will divide out with one of these, and I'll be left with units of meters, which is what I would be expecting. Now when I look at this value, the magnitude of my value, it's quite small. I was expecting it to be small with the magnitude of the numbers that I plugged into my equation. But if I'm thinking about this in terms of the wavelengths of light that exist on the electromagnetic spectrum, this is a very small wavelength, quite small. So small that it's physically improbable because our highest energy, so our lowest wavelength light, is our gamma light, right? It's gamma radiation. Gamma radiation sits at orders of magnitude of around 10 to the negative 13th meters in terms of wavelength. So those are also quite small, but you can see then that this wavelength is so improbably small, it's not even on the electromagnetic spectrum. So it's not even really light at this point because it doesn't even exist in a wavelength that fits into our concept of what light can be. So this is more of an intellectual exercise more than anything else when we're talking about particles this size, right? When if I'm talking about the mass of something like a bowling ball, I could calculate its wavelength. It would give me something even smaller than this, but it's just not physically probable, right? It doesn't physically make sense for something to be off of the electromagnetic spectrum in terms of wavelengths. But again, you can do the calculation. This is the model that we're using. And then if you go in the opposite direction and get particles that are more and more tiny, so now we're in the age of more subatomic particles. We think about things in terms of quarks now, and even smaller particles within the particles of our nuclei, within the other subatomic particles, muons, all these kinds of things that are building up from an even smaller level. Now, these are on the order of things that we can actually calculate wavelengths for, and they have wacky quantum mechanical behavior that comes about because of this energy or wave nature of the particles. But for our purposes, as those of us who are thinking macro scale, or even those of us who are chemists who are thinking in terms of, atomic scale, we're still at a very large level compared to where these calculations are really useful and critical. But it's kind of an interesting intellectual exercise, and it comes from the premise really that if we can think about light as both wave and particle, why can't we go the opposite direction, right? Why can't we think of particles as waves? And that's de Broglie in a nutshell.